So let's consider the limitations in experimental calorimetry, that is measuring energy changes, in the two common methods that we see in IB chemistry. The first is measuring the enthalpy change of combustion, normally of some kind of fuel. So there's my spirit burner containing a fuel, perhaps it's an alcohol, and to measure the energy released by that reaction, we often do this underneath a calorimeter containing water, so that I can measure the temperature change in my water, which is the surroundings in this case, and calculate how much energy has been released by the reaction underneath. There are two major limitations to this methodology. The first one is heat loss to the environment. And specifically what we're talking about here is energy loss to the air around that reaction, not transferring directly into my calorimeter. The second limitation that we need to be aware of is heat loss in terms of the energy absorbed by the calorimeter itself, often made of copper, which we're not taking into account in our calculations. Depending on the material used for the calorimeter, it might absorb different quantities of energy during the reaction. The second method we often see is calculating an energy change of a reaction occurring in a solution. So in this case, my reactants and products would all be in the water instead of underneath it. So the purple and yellow particles are just representing my reactants and products from the chemical reaction taking place. So what are the limitations in this method? Well, the first one, similar to before, is that even though we use an insulating material for the calorimeter, such as a polystyrene cup, we are always going to have some heat loss to the environment. And in this case, the environment would be the air outside of that polystyrene cup. Secondly, for our calculation, we are assuming that 1 centimetre cubed of this solution has a mass of 1 gram. Now that's true for pure water, but as soon as I have a solution with other things dissolved in the water, that is no longer going to be the case. But in general, it's accurate enough for IB chemistry. Thirdly, also related to our calculation, the value for the specific heat capacity of pure water we use is 4.18 joules per gram per Kelvin. But again, in this case, because I have a solution that's not pure water, that's not going to be 100% accurate. In summary, both methods have limitations, which means that this approach to calorimetry will not always be 100% accurate. And you might need to use or discuss these limitations in exam questions and also your internal assessment if relevant to your experiment. Hopefully this video was of some help.